Howdy. This video is on acid-base theories. Acid-base theories provide a framework for understanding a lot of different reactions. The theories are conceptual tools that will help you understand how some compounds react and why some reactions have larger Ekman constants than others. After watching this video, you should be able to distinguish between the three acid-base theories and identify when they can be applied. You should be able to identify the differences between a strong acid and a weak acid. You should be able to identify the differences between a strong base and a weak base. You should be able to recognize strong acids and strong bases. You should be able to recognize polyatomic ions and their behavior. And you should be able to relate acid-base chemistry to equilibrium constants. Due to the extremely large number of compounds, chemists develop models and ideas of how to think of compounds and their reactivity. There are literally tens of millions of distinct compounds with distinct chemical and physical properties. Now we can imagine we could characterize compounds by their ability to donate or accept protons, which are just hydrogen ions, and that would be the Bronsted-Lowry theory of acids and bases. We could also characterize compounds on their ability to donate or accept a pair of electrons, and that corresponds to Lewis' theory of acids and bases. And so there's three common acid-base theories: the Arrhenius, the Bronsted-Lowry, and the Lewis. Of these three, the Arrhenius theory was developed first. It is the simplest. It defines an acid by what happens when you add a compound to water. If you add a compound to water and hydrogen ions are produced, then it's characterized as an acid. If you add it to water and hydroxide ions are produced, then it's characterized as a base. Bronsted-Lowry and Lewis theories are a little bit different. They look at a reaction, and in a reaction is something behaving like an acid or a base. Lewis theory is more general. It can actually handle aqueous solutions as well as non-aqueous solutions and even solid-solid reactions. Arrhenius theory is just when we're looking at aqueous solutions. So Bronsted-Lowry theories, you're looking at if in a reaction it accepts hydrogen ions, then it's characterized as a base. If in a reaction it donates hydrogen ions, then it's characterized as an acid. And Bronsted-Lowry theory is great for aqueous solutions. For Lewis theory, if in a reaction a compound accepts an electron pair, then it's characterized as an acid. If in a reaction a compound donates an electron pair, then it's characterized as a base. And again, Lewis theory is the most general. And again, Bronsted-Lowry and Lewis theories, you're looking at a reaction. In a reaction is something behaving like an acid or a base. Arrhenius theory, because you add it to water, you look at what happens. According to Arrhenius theory, if something's an acid, it's always an acid. Now, Bronsted-Lowry and Lewis theories are consistent. All Bronsted-Lowry acids are Lewis acids. But because Lewis theory is more general, not all Lewis acids are Bronsted-Lowry acids. And so when we talk about strong acids, weak acids, strong bases, weak bases, we're using Arrhenius theory. Strong acids are characterized as those compounds that completely dissociate, meaning that basically 100% of the acid molecules break apart into ions.
An acid is a substance that produces hydrogen ions when dissolved in water. Hydrogen chloride is an example of a common and important acid. When hydrogen chloride gas dissolves in water, it forms hydrochloric acid. Hydrogen chloride is very soluble in water and is completely dissociated. It is therefore a strong electrolyte. Nitric acid is another common strong acid. Upon dissolving in water, nitric acid completely ionizes to form an acidic solution. Like hydrogen chloride, nitric acid is a strong
electrolyte. And so when you add it to water and something breaks apart into ions, 100% of those molecules, we refer to that as a strong electrolyte. All strong acids are strong electrolytes. And so nitric acid, HNO3, is a strong acid. Pretty much 100% of the nitric acid molecules break apart into hydrogen ions and nitrate ions when you add it to water. Now we can define the Ekman constant that describes this reaction as a Ka of nitric acid. Ka means acid dissociation constant, and so think about it, acid dissociating, acid breaking apart, and so the acid is the reactant, and then the ions are the products. Now for strong acids, we can consider the Kas as basically infinite. Now we can write it as an acid breaking apart into hydrogen and nitrate ions. We can also write it as the acid plus water forming hydronium ion and the chloride ion. And so the hydrogen ion and hydronium ion are the same thing. On average, a hydrogen ion in water is surrounded by 4 water molecules. And so the hydrogen ion and the hydronium ion are basically shorthand ways of writing hydrogen ion with 4 water molecules.
Strength of an acid refers to the extent that it dissociates into ions when dissolved in water. Strong acids dissociate nearly completely. Weak acids dissociate very slightly. Dissociation into ions means that when an acid, Ha, dissolves in water, it transfers a proton to one of the water's lone electron pairs, and the acid anion, A-, and a hydronium ion, H3O+, form. The color change of the water oxygen will make it easier to follow in solution later. The key difference between strong and weak acid dissociation is the final concentration of hydronium ion in solution. Since proton transfer from a strong acid to water is nearly complete, the hydronium ion concentration is essentially the same as the original acid concentration. In contrast, proton transfer from a weak acid to water becomes balanced by proton transfer from hydronium ion to A-. So the final hydronium ion concentration is much less than the original acid concentration.
And so strong acids completely dissociate, meaning 100% of the molecules break apart. Weak acid, only a very small fraction of those molecules actually break apart.
Let's view acid dissociation at the molecular level and focus first on strong acids. The concentrated acid in the beaker consists primarily of acid molecules. As soon as they make contact with the water in the flask, proton transfer from Ha to H2O occurs for virtually every acid molecule. Note the change from blue to red. Therefore, a strong acid solution consists of hydronium and A- ions in water and virtually no Ha. It follows that the acid dissociation constant Ka for a strong acid is very large.
And so please remember Ka stands for acid dissociation constant, and so that's the Ekman constant for the acid forming the ions, and so the acid would be a reactant. Now I mentioned that hydrogen ion and hydronium ion refer to the same thing. On average, a hydrogen ion is surrounded by 4 water molecules.
A water molecule consists of 2 atoms of hydrogen and 1 of oxygen. Water molecules are attracted to a hydrogen ion, or proton, to form a conglomeration. There are often 6 and sometimes more water molecules around an ion. Because the hydrogen ion is so small, it is thought to have an average of 4 water molecules associated with it at any time.
And so because we can treat the hydrogen ion and hydronium ion as the same, these two reactions are equivalent. Remember, pure solids, pure liquids do not appear in equilibrium expressions, and so for these two reactions, you'd have hydrogen ion times chloride ion divided by HCl. Here you'd have hydronium ion times chloride ion divided by HCl. Because hydrogen ion and hydronium ion are the same thing, those two reactions are equivalent. They have the same equilibrium constant. And so strong acids completely dissociate. Weak acids only partially dissociate, meaning only a small fraction of the weak acid molecules actually break apart.
Acetic acid is the major ingredient of vinegar. When acetic acid is added to water, it is not completely ionized. It is therefore termed a weak electrolyte, or weak acid.
And so weak acids, only a small percent of the molecules actually break apart. And so for a weak acid, the Ka is really small. We'd say the reactants are much more stable than the products.
Now the beaker contains a weak acid. As before, the moment the acid molecules make contact with the water, proton transfer from HA to H2O occurs. But in a very short time, proton transfer from hydronium ion to A- balances it, and equilibrium is reached. Thus, a weak acid solution has a relatively high concentration of HA and very low concentrations of H3O+ and A-. Therefore, the acid dissociation constant is very small.
And so for a strong acid, we treat it as if it completely disassociates. And for a weak acid, a very small percent disassociates. Weak acid, you have a very small Ka. Strong acid, we actually treat the Ka as if it was infinite. And again, the Ekman constant for dissociation acid is referred to as the acid dissociation constant. So that means the acid is the reactant and it's breaking apart. We can characterize the strength of an acid by looking at its relative value of the Ka. We could also ask what is the concentration of HCl molecules and hydrogen ions and chloride ions in a 1 molar solution of HCl at equilibrium. And so if we think about it, we can write down the reaction. So HCl going to hydrogen ions plus chloride ions. It's a strong acid, so it completely disassociates. And so if we start with 1 molar HCl, we actually end up with 1 molar hydrogen ion and 1 molar chloride ion. And so a bottle labeled 1 molar HCl contains no HCl molecules. And so notice that 1 molar HCl refers to a solution, and HCl in a reaction refers to a molecule. But again, a bottle labeled 1 molar HCl has no HCl molecules because all the molecules broke apart. We could also be asked what is the concentration of HF molecules and hydrogen and fluoride ions in a 1 molar solution of HF at equilibrium. And so likewise, we can write down our ICE table. Initial change equilibrium. We're starting with 1 molar HF. Initially, we have 0 hydrogen ions and fluoride ions in the beaker. When X HF breaks apart, we'll get X of hydrogen ions, X of fluoride ions. In the equilibrium is initial plus a change, so 1 minus X, X, and X. Now, because Ka is really, really small, remember that means the reactants are favored. We have mostly reactants at equilibrium, and so most likely X is going to be negligible compared to our 1. And so we can make the approximation that X is negligible compared to 1. Now, here's our Ekman expression. Products over reactants, coefficients become exponents, pure solids, pure liquids do not appear. And so we can plug in X and X for the hydrogen ion concentration, fluoride ion concentration, and 1 for HF. And so that gives us Ka equals X squared divided by 1. And the Ka was 3.5 times 10 to the minus 4th. And so if we take the square root, we get that X is equal to 1.9 times 10 to the minus 2. And so that's the hydrogen ion concentration and fluoride ion concentration at equilibrium. Now, we solve this problem using our approximation, and typically we should be able to use approximations when we're doing weak acids. And if we look at it, our approximation was good. 1.9 times 10 to the minus 2 is a lot smaller than 1. Now, we could have also done it using the quadratic equation. And so here we have X times X divided by 1 minus X equals our Ka. And then if we do a little bit of math, we can get our quadratic equation, x squared plus 3.5 times 10 minus 4x minus 3.5 times 10 minus 4 equals 0. And so you can solve the quadratic equation using this equation here. You notice that because of that plus minus, you'll get 2 answers. One will not be reasonable, the other one will be. And so our 2 answers are here. And so notice that you cannot have a negative concentration, and so the negative number is not reasonable. And so we get 1.95 times 10 to the minus 2. Now, if you remember, using the approximation, we had 1.9 times 10 to the minus 2. And so the 2 answers were equivalent. for a weak acid problem, typically you should be able to use the approximation. It's also kind of interesting. We can ask, of the acids on the left, which is the strongest? And so it's going to be the one with the largest Ka, and so that corresponds to HiO3. The weakest corresponds to the one with the smallest Ka, which is HCN. And so please remember, Ka indicates the strength of the acid. And so I want you to remember the 7 strong acids. You have nitric, sulfuric, hydrochloric, chloric, perchloric, hydrobromic, and hydroiodic. Now, inorganic acids are written with hydrogen as the first element, so like HCl. And so you can recognize these as acids because they have H in the front. Now, it's kind of interesting if we look at sulfuric acid. Sulfuric acid is a strong acid because it easily loses that first hydrogen. Now, once you lose the first hydrogen, then you have hydrogen sulfate. Now, hydrogen sulfate is a weak acid because you don't lose that one so easily. And so notice that the Ka for hydrogen sulfate is pretty small. And so it's just that first hydrogen that comes off easily. Now, the Ka's, the strong acids, are pretty difficult to determine. We treat them as infinite. They're not actually infinite. You know, Hi is 10 to the 11th, HClO4 10 to the 10th, HBr 10 to the 9th, and HCl 10 to the 7th. But again, typically, we treat the Ka's of strong acids as infinite. You know, if you have a bottle labeled 1 molar Hi, you have no Hi molecules. You have just hydrogen ions and iodide ions. Now, acid names are related to the anion, and so nitric acid, and without the hydrogen, you have the nitrate ion. Notice that the nitrate ion has a -1 charge, and so nitric acid, you have 1 hydrogen to make this neutral. The sulfate ion, you have a 2-, and so that's why sulfuric acid has to have 2 hydrogens. The name is related to the acid is related to the name of the anion. And so notice that nitric, ic, you have 8. Ic corresponds to 8. Per-ic corresponds to per-8. Now, I don't expect you to memorize a list of weak acids, but I want you to be able to recognize the weak acids. And so the hydrogen in front corresponding to an acid, but they're not on your list of strong acids, and so they must be weak acids. Now, COOH is a little bit different. That corresponds to an organic acid, and all organic acids, like organic professors, are weak. And so if you see COOH, please remember that corresponds to a weak acid. Also remember that, you know, sulfurous acid is a polyprotic acid. It has multiple acidic protons, but it's still a weak acid because the strength of the acid depends on the Ka. Phosphoric acid has 3 acidic protons, but it's still considered a weak acid because the Ka is still very small. And the ability to remove subsequent hydrogen ions gets harder and harder. And so to remove that first hydrogen is the easiest. To remove the second hydrogen gets a little bit more difficult. To remove the third hydrogen gets even more difficult. And again, the charge indicates the number of hydrogen ions. And so phosphate ion, you have a -3 charge. And so that's why phosphoric acid, you need 3 hydrogens. And again, the name of the acid is related to the name of the anion. And so we have sulfuric, gives us 8. Sulfurous gives us ite. Ic, 8. Us, ite. Now, there are a couple series that have 4. And so you have perchloric, chloric, chlorus, hypochlorus. And so these names are related to the relative number of oxygen. And so if you start with the fewest number of oxygen, which would be hypo-us, then you go to us, ic, and then per-ic. Now, it's a little confusing because, you know, if you look at nitric acid, it's got 3 oxygens, while sulfuric has 4 oxygen. And so again, it's relative number of oxygen. the ik will always have one more oxygen than the us. And again, you should know these polyatomic ions. They're important. They stay together as a group. And so we have to be able to recognize them. And so polyatomic ions stay together as a group. So nitrous acid, it'll break apart into hydrogen ions and nitrite ions. Calcium hydroxide breaks apart into calcium ions and hydroxide ions. And so we talked about acids. According to Arrhenius theory, acids are defined, if you add it to water, it produces hydrogen ions, it's an acid. According to Arrhenius theory, if you add it to water, it produces hydroxide ions, then it is a base. Now, strong acids completely dissociate, meaning that all the molecules break apart. Strong bases completely dissociate, meaning all the molecules break apart.
Bases are substances that increase the concentration of hydroxide ion in water. Water-soluble ionic hydroxides, such as sodium hydroxide, potassium hydroxide, and calcium hydroxide, are among the most common bases. When sodium hydroxide is dissolved in water, it completely dissociates into sodium and hydroxide ions. Because sodium hydroxide is completely ionized in solution, it is referred to as a strong base. It is also, of course, a strong electrolyte.
And so because 100% of the sodium hydroxide breaks apart into ions, we call it a strong electrolyte. I noticed that the products are a lot more stable than the reactants, and so the Kb, we treat it again as infinite. Now for a weak base, it's a little bit different. For a weak base, it doesn't have any hydroxide to start with. The hydroxide is formed by the weak base ripping off a hydrogen ion from water.
Ammonia does not contain the hydroxide ion, but is basic in water. When gaseous ammonia dissolves in water, it reacts with water to form the ammonium and hydroxide ions. However, ammonia is a weak base. The equilibrium forming the hydroxide and ammonium ions lies largely to the left. At any given time, most of the ammonia is in a non-ionized form.
And so it's a little confusing. This reaction would say that can cause the Kb for ammonia, and its Kb stands for base dissociation, but it's not, the base is actually not breaking apart, right? So the ammonia is ripping off the hydrogen ion from the water, and that's how that hydroxide is produced. And even though the base is not breaking apart, we still refer to the Ekman constant for this reaction as a Kb, base dissociation. And so weak bases have small K sub B's. The reactants are a lot more stable than the products. Now I think about ammonia as our typical weak base. It's got this lone pair, and it uses the lone pair to rip off the hydrogen ion, producing the hydroxide ion. And so it's a great way of thinking about Lewis theory and Bronsted-Lowry theory. And so because ammonia is donating the electron pair, we call it a Lewis base. Because it's also accepting the hydrogen ions, it's also a Bronsted-Lowry base. Because you add it to water and it produces hydroxide ions, according to Arrhenius, it would also be a base. And so according to all three theories, ammonia is a base. Now this shows you one value of the electron density, that's the surface. Then the color corresponds to electrostatic potential, and so the red is partial negative, the blue is partial positive, and so you see that lone pair, and it's the lone pair that makes ammonia our typical weak base. And so strong bases completely dissociate, their Kb's are really, really large. They're strong electrolytes. Weak bases, their Kb's are much smaller, only a very small fraction actually react. And again, we can use Kb to characterize the strength of a base. And so what is the concentration of sodium hydroxide molecules and sodium ions and hydroxide ions in a 1 molar solution of sodium hydroxide at equilibrium? And so all the sodium hydroxides breaks apart. And so if we start with 1 molar sodium hydroxide, we end up with 0 sodium hydroxide. We end up with 1 molar sodium ions, 1 molar hydroxide ion. And so again, it's really a little confusing, a bottled labeled 1 molar sodium hydroxide contains no sodium hydroxide molecules, just contains 1 molar sodium ions and 1 molar hydroxide ions. We could also be asked what's the concentration of ammonia molecules, ammonium ions, and hydroxide ions in a 1 molar solution of ammonia. And so again, we can make our ice table. Now our K is really small, and so we can assume that X is negligible compared to 1, similar to what we did when we talked about the weak acid. And now we can plug in these to our Ekman expression. And so x times x divided by 1, so we have x squared divided by 1 equals 1.8 times 10 minus 5. If we take the square root, we get x equals 4.2 times 10 minus 3. Now this is really small compared to 1, so our approximation was good. And so in a bottle labeled 1 molar ammonia, we'd have basically 1 molar ammonia, and we'd have 4.2 times 10 minus 3 molar hydroxide ion and ammonium ion. Now, just like we could do the quadratic equation for the weak acid, we can also do it for the weak base. So again, if we plug in the concentrations to our Ekman expression, we get this. If we do the math, we can get this Ekman expression, the quadratic equation. We solve the quadratic equation using this. Plus or minus means we have 2 values. One is going to be possible, one is not. And so we end up with 4.23 times 10 minus 3. Now when we did the approximation, we got 4.2 times 10 minus 3. And so our approximation value was consistent with the value from the quadratic equation. And so for weak acids, weak bases, typically we should be able to use the approximation. The base on the left, which is the strongest, and so we can use the Kb to characterize the strength of the base. The bigger the Kb, the stronger the base. The smaller the Kb, the weaker the base. And so I want you to know the strong bases. And so the alkaline metal hydroxides are all strong bases, and the heavy alkaline earth hydroxides are strong bases. Remember, strong electrolytes form solutions in which a solute is present almost entirely as ions, and so all strong acids and strong bases are strong electrolytes. Weak electrolytes, only a small fraction of solute molecules break up into ions. So what species are present in the following solutions at what concentration? And so we should recognize lithium hydroxide is a strong base. And so it's going to be present as 1 molar lithium ions and 1 molar hydroxide ions, and you'll have 0 lithium hydroxide. HCl is a strong acid, and so 3 molar HCl is going to be 3 molar hydrogen ions, 3 molar chloride ions, and 0 HCl molecules. We could also be asked to calculate the hydroxide ion concentration for a 0.01 molar ammonia solution. And so again, we'll want to recognize first that that's a weak base. And so we write down the reaction of water plus the weak base going to the ammonium ion plus hydroxide ion. We can make our table. So initially we have 0.01 molar ammonia, 0 of ammonium ion, 0 hydroxide ion. When X reacts, we'll get X ammonium ion, X hydroxide ion. Equilibrium is initial plus a change. Now our K is really small, so most likely X is negligible compared to 0.01. Now we plug this into our Ekman expression. And so our Ekman expression, we have ammonium ions times hydroxide over ammonia. So X squared divided by 0.01. And so multiply both sides by 0.01. Take the square root, and we get that the ammonium ion concentration is 4.2 times 10 minus 4. The hydroxide ion concentration is 4.2 times 10 minus 4. And so our approximation was good because X is much, much smaller than 0.01. And so there's 3 common acid-base theories: Arrhenius, Bronsted-Lowry, and Lewis. Both the Arrhenius and Bronsted-Lowry theory are focused on defining acids based on hydrogen ions and hydroxide ions. And when we're talking about something that's strong acid, strong base, weak acid, or weak base, we're using the Arrhenius theory. And remember, the larger the Ka, the stronger the acid. The larger the Kb, the stronger the base. I hope that helps.